This is Geometry Lesson 1.6, Betweenness and Distance. So the big idea says the distance between 2 points is measured along the coordinate line that contains them and obeys rules that are summarized in the distance postulate. All right, so we're going to be looking at the distance between points, what points are between other points on a line, talk about different kinds of lines, such as rays and segments, opposite rays, and talk about finding distance between points on a line. So first of all, the word between, we want to go ahead and define that in terms of geometry. We know obviously what the word between means, but specific to what we're looking at, that's going to be a point So a point is between two other points if it's on the same line and its coordinate is between their coordinates. Let's go ahead and zoom out further. There we go. All right, so a point is between two other points if it's on the same line and its coordinate is between their coordinates. So obviously if we have 2 points like this, right, that are on the same line, a point that's up here would not be considered between them. The point has to be on the same line. Okay, that's why we had that first part. And the coordinate needs to be between their coordinates. So if this was 0 and this was 10, it would have to be between 0 and 10. It can't be less than 0 or more than 10, or it's not between them. So it has to actually be on the line that's between the 2 points, and the coordinate needs to be between them. Now, if I was going to show the possible coordinates that could represent a point between these, let's call it x, we would say x has to be greater than 0 and less than 10. So any number in here has to be greater than 0 or less than 10. It can't equal 0 if it's between them. It's got to be greater than or less than. All right, and now we're going to talk about segments and rays. So a line goes forever in both directions. A segment does not. A segment has endpoints. So a line, if I was going to write the name of a line, I put the endpoint letters and I draw a line above it with arrows going both ways. That's just your normal line that goes forever in both directions. So if this was A and this was B, you could name that just like that. Now a segment is going to just have a line like this with no arrows on it, because that's what a segment actually is. So it stops. It doesn't go forever in both directions. So if I was on a number line, well, I don't even want to put the arrows on the number line because I want you to see that there's endpoints here. So we've got A and B, and there's nothing else that goes to the left or to the right of them. So the actual definition here, the points A and B, so those are your points, and all the points between them. Let's keep these separated here. So very simple. You've got 2 endpoints. It doesn't go forever in both directions. So the segment is both of those points and then every point that is between them. That's a segment. All right, a ray has one endpoint and then goes forever in the other direction. It can go to the left, it can go to the right, but it has an endpoint and then goes forever. So this has 2 endpoints, a line has no endpoints, goes forever in both directions, and a ray goes forever in one direction. So our definition here, we have an endpoint and all the points on one side of that endpoint. Now when we name these, we have to start with the endpoint. So you can see I've got the arrow going this way. I know that this ray, right, if it starts here and then goes forever this way, I know that this point right here is A. And I know that B is somewhere on this. It's going to go through B. It's not going to end at B. That would be a segment. It's going to go through B and go on forever. But it is very, very important when you name a ray. You couldn't call this ray BA because it doesn't start at B. It starts at A. We show that that's the endpoint, and the arrow goes through B. All right, now opposite rays. Those are rays with the same endpoint that go in opposite directions. Okay, so same endpoint. So they're both going to start at the same spot, and we'll call this A. One goes this way. Let's call this B. And then another ray goes this direction. And let's just call this C. So if I was going to name the opposite rays here, it's AB and AC. Notice how both times I started with the letter A because that's the starting point. Okay, this is AB, starts at A, goes forever through B. And this is AC, starts at A and goes forever through C. If you call this CA like this, you're talking about a different ray. That's the one that starts right here and goes forever this way through A and then eventually through B. That's CA, which is not the opposite ray we're talking about. So we're talking about the ones that start at the same spot. One goes this way, that's AB, and one goes this way. So we also have opposite rays over here. We couldn't name this one because we don't have another point out here. But if there was another point, you could say C going this direction and C going this direction. Those are opposite rays. And same thing here. Going this way from B and going this way from B. Those are opposite rays. All right, distance postulate. Again, postulate we talked about the last section is an assumption. So we've got some assumptions we can make here. Some of these we've already talked about. So 3 parts to this. First one says on a line, there is a unique distance between 2 points. And I am really squeezing this in here. So if you're on a line and there's 2 points, there's a unique distance. There's a distance between those 2 points. It can be measured. That's what it says. That's the assumption. We can measure the distance between 2 points if they're on a line. That distance, part B, can be measured using our distance formula. Subtract the 2 points, take the absolute value. Give a positive number for a distance. So the first 2 parts. Any 2 points on a line have a unique distance, meaning one specific distance between them. And that distance can be measured by x minus y, take the absolute value. All right, and the last part of this distance postulate, something we're allowed to assume, it's called the additive property. And we'll look a lot at this today. So if B is on segment AC, so let's picture this for a second. You've got segment, meaning there's endpoints, AC, and B is on this. B is somewhere in the middle. Doesn't have to be directly between them where it's equal on both sides, but it's somewhere on this line. So if B is on AC, the additive property says we know we can assume AB plus BC equals AC. So let's make sense of this. AB is this distance, and BC is this distance, and then AC is the whole thing. So if B is on this segment, it's between A and C on this line segment. We know that it's kind of breaking this into two pieces. Those numbers, if I add them up, is going to give me the distance of the entire line segment. So if the whole thing was 10 and this is 3, I know this is 7 because 3 plus 7 has to give me the whole thing. So no matter where I put B, it's going to break this into two pieces that add up to the same distance of the entire length. Okay, a couple practice problems now. So we're going to draw GH. Important to notice this is a line. You have arrows on both sides. So I'm going to put G, and I'm going to put H, and this is a line that goes through them and forever in both directions. Now if I draw JK, that's a ray, right? No arrow on this side. So that's going to be my starting point. It's going to go forever in one direction. It could go the other way too, but I have to start at J. That's what this notation is telling me. It starts at J, that's my endpoint, and goes through K forever. ST, that's a line segment, no arrows. So I have 2 points, S and T, and they're just connected. Those are the endpoints, doesn't go past them. Number 4, we're going to name this line in 3 different ways. You can pick any letters. This is a line, not array. And so you can use any letters because this line passes through all of them. So I could use these two right here. I could call this line UV. I could pick the ones that are farthest apart, UY. I can pick another 2 letters, WX. You could use VW and VX and VY, WY, UW. Any 2 points on this line can be used to name it because we're not talking about endpoints here. We're not talking about array. So just specific to lines, they go forever in both directions. You can pick any 2 points to name it. All right, using this same figure, name opposite rays. Lots of ones we can use here. Let's use W as our endpoint. You could use other ones. So opposite rays. So I have to start with W, and then you could say X or Y. If I'm going this direction, I'll say X. I draw it like this. This means I start at W and I go towards X. And if it's an opposite, it also has to start with W and go the opposite direction. It can't go this way. Just because it starts at W and goes a different direction, that's not an opposite. Okay, an opposite ray goes directly the other way on the same line. And so that would be WV or WU. Either one is fine. This would be good. Let's name one more pair here. Let's talk about the ones that maybe start at X and go each direction. So this way would be XY. Again, have to start with X. And then this direction, I can call it, I have to start with X because that's the endpoint. And then it goes forever through all 3 of these points. So I could call it XW or XV or XU. It doesn't matter. But XY goes this way, XV goes this way, both starting at X. Those are opposite rays. Okay, and then the last 2 questions we're going to look at here go to our additive properties. So we've got a segment and it's broken into pieces, but we know that all of these pieces have to add up to the whole thing. The distance from P to S is going to be equal to all of these little distances put together, added together. That's why it's called the additive property. So let's label what we have here. PR, this distance, is 25. QS is 30. And PS, the whole thing, is 37. And now we need to go find these. We got to find PQ, QR, and RS. So the first thing I notice is, okay, the whole thing's 30, and all of this, the whole thing's 37, and all of this is 30. So all I'm missing is this little piece right here, and I have all of it, which is 37. So if this is 30, this must be 7, so that together they make 37. So PQ is 7. Once I know this is 7, now I'm going to just look at this segment. PR is 25, PQ is 7. So all I'm missing is this piece. This piece plus 7 has to equal 25. So you would subtract them, 25 minus 7. It's 18. Double check yourself. 18 plus 7 is 25. So these two pieces together have to equal the whole thing. So QR is 18. And now RS. So again, we go back to this piece right here. We know it's 30. From Q to S is 30. And from Q to R is 18. So RS, our missing piece right here, has to add together with 18 to get me 30. So you just do 30 minus 18. That must be 12. 12 plus 18 gives me 30. Flip it over. The last thing we can do is look at these with some algebraic expressions put in there and then solve them by writing an equation. So let's go ahead and put these into the picture. PQ, this distance is 3x. QR is 8x minus 2. RS, 4x plus 1. And PS, the whole thing, is 29. And we want to go find these distances now. How are we going to do that? So we need to set up an equation. If we just set up some things with these, I don't think we're going to be able to figure out the actual distance. The only actual distance we have here is 29, so we're going to have to use that somehow. If you knew that these were equal to each other, you could set them equal and solve, but clearly they're not, and you'd be guessing if you said these were. So the only equation that I see that we can set up is the fact that I know if I add up all three of these pieces, let's pretend I knew what they were. Like maybe this was 10, maybe this was 15, or something like that. If I add them all up, they have to come out to 29. So I'm just going to use those expressions, this plus this plus this plus this has to equal 29. Has to. If I add up the three pieces, it has to equal 29. So I'm going to write that out algebraically. 3x plus 8x minus 2 plus 4x plus 1 equals. If you want to put parentheses around them so that it makes you feel comfortable that you've got all three of them, you can, but you don't have to. So this plus this equals 29. That's a true equation according to our additive property. All right, so now we just have to go ahead and solve this. Pretty straightforward. Combine all your x's, they're on the same side of the equal sign. 8 and 4 is 12, plus 3 is 15x. Combine like terms here, -2, +1. That would be a -1. So all I did on the left side of the equation was combine like terms. Put your x's together, 15x. Put your whole numbers together, -1. And now we've got a basic equation, just solve it. So add 1 to both sides and divide. So x equals 2. Now I haven't answered the actual question yet, so let's go back and solve. PQ is equal to 3x. Well, we just found out x equals 2, so we're going to plug it in. 2 goes in for x. 3 times 2, so PQ equals 6. QR, that's equal to 8x minus 2. I'm going to plug my answer of 2 in for x, so it's 8 times 2 minus 2. 8 times 2 is 16, minus 2 is 14. So QR is 14, and then RS, 4x plus 1, plug the 2 in, 4 times 2 plus 1. 4 times 2 is 8, plus 1 is 9. And I would always double check those, right? We know they have to equal 29. So if I've done all my work correct, if I add these up, they will equal 29. If they don't, I know something's wrong. I've made a mistake somewhere. But 14 plus 6 is 20, plus 9 is 29. 6 plus 14 plus 9 equals 29. My work checks out. This is good to go.